Good morning, guys. In continuation to the last topic, Coulomb's law. Okay, force in terms of rectangular coordinates are there here. Okay, what is the conclusion from that Coulomb's law? What is the statement of that Coulomb's law? Coulomb's law states that actually why it is called a Coulomb's law? Who invented this relation? Charles Augustin de Coulomb. Actually, he is a French army engineer. Okay, that's why it's named as a Coulomb's law. Okay, Charles Augustin de Coulomb. Remember that point. Okay, according to his opinion, the attraction or repulsion forces between the 2 point charges. Okay, and the point charges are located in a space. Just assume 2 point charges located in a space. Okay, but because of that polarity, okay, for suppose they are opposite polarities, they attract each other. If they are identical, I mean the polarities are same, then repel each other. Okay, that is the basic fundamental. Okay, the attraction or repulsion forces between the charges is always proportional to uh, their magnitudes. Okay, the charge magnitudes q1 and q2. Okay, is proportional to charge magnitudes q1 and q2, or simply the product of q1 and q2, and inversely proportional to distance between them. And f is inversely proportional to 1 by r square. And f proportional to q1 into q2, f inversely proportional to 1 by, I mean, f is proportional to 1 by r square. Okay, when we combine these two, f proportional to q1 q2 by r square. But when we this situation is considered under the free space. Okay, that's why that free space constant is also considered here as a k, where k equal to 1 by 4 pi epsilon naught. Okay, actually epsilon naught and epsilon r, where epsilon r is the relative permittivity of free space is 1. That's why 1 by 4 pi epsilon naught only visible here, where epsilon naught is the 8.854 in 10 power minus 12. Okay, all these are recap only. Okay, that is the basic relation. Okay, already in yesterday's class, okay, you see one problem also. Okay, everything is depends on Coulomb's law. Okay, see here force in terms of rectangular coordinates. Okay, in today's topic, okay, force in terms of rectangular coordinates. Okay, and problem on that, and force due to n number of charges. And so far we learn what is the resultant force due to point charge, right? 2 point charges. And when we consider the 2 point charges, at that time only we define this Coulomb's law. But here the case 2, as when we consider n number of charges, what is the resultant force? Okay, of course the algebraic sum of that okay, point to point force. See here. See here, force in terms of rectangular coordinates. What are the rectangular coordinates? What is the alternate name of rectangular coordinates? Okay, Cartesian coordinate system or rectangular coordinate system, both are same in that x, y, z three-dimensional view is used to analyze that okay, point in a space, right? See here, consider the 2 point charges q1 and q2. Those are located at two different points called x1, y1, z1. Okay, located at a point x1 y1 z1 and x2 y2 z2. And these 2 points, of course, these two are the combination of xyz combinations and intersecting points, right? This is the point A and this is the point B. Point A location is the intersecting point of x1 y1 z1, and point 2 is the intersection point of x2 y2 z2. Okay, now okay, and in terms of rectangular coordinate system, how they are represented. Okay, see here, now the distance vector. Okay, the distance vector of a from origin of r1 equal to x1 into ax, y1 into ay, z1 into az. Of course that ax, y, az are unit vectors. okay, or similar distance vectors. Similarly, from the B, okay, R2, okay, and from the origin, consider origin, okay, origin to Q1 and origin to Q2. From origin to Q1, the notation x1, y1, z1. From the vector B, x2, y2, and z2, okay, are the unit vectors. The unit vectors of R1 and R2, how they represented unit vectors? Unit vectors along the direction of R1 is R1 equal to magnitude of R1 by, distance vector of R1 by, okay, mod R1, okay. So x1 into ax, y1 into ay, z1 into az by its mod, square root of x square plus y square plus z square. Okay, similarly R2, square root of x2 square plus y2 square plus z2 square. Okay, the distance vector from A to B. Okay, the distance vector from A to B is R2 minus R1, right? So x2 minus x1 whole square into ax, y2 minus y1 whole square. Okay, x2 minus x1, y2 minus y1, z2 minus z1, right? There is the distance vector. So the unit vector along the 1, 2 direction is, okay, this R12 vector, distance vector by mod, its mod value, and the square root of x2 minus x1 whole square, y2 minus y1 whole square, z2 minus z1 whole square. Okay, I think you are all aware of, okay, these relations. Okay, according to the Coulomb's law, okay, what is the attraction or repulsion forces between the point charges, okay, Q1 and Q2? Okay, from the fundamental relation F equal to Q1 Q2 by 4 pi epsilon naught. Okay, F equal to Q1 Q2 by 4 pi epsilon naught into, okay, JR12, right? Okay, unit vector along the R12 direction. Okay, F equal to Q1 Q2 by 4 pi epsilon naught. Of course, that R square into AR of 1 2. That is the fundamental relation we derived in the main derivation, right? So x2 minus x1, okay, the same relation is substituted here. Okay, the same relation is substituted here. Okay, AR12 is substituted here. X2 minus x1 in dx, y2 minus y1, z2 minus z1. Similarly, x2 minus x1 whole square, y2 minus y1 whole square, z2 minus z1 whole square. Of course, here q1 q2 by 4 epsilon not r square, right? Here r square means r12 whole square. R12 whole square into that R12 is the mod R12 is the under root of, this is the square and this is the additional one, right? Under root over 1 by 2. So total is 3 by 2. Okay, that's why we get 3 by 2 here. Is it clear? Okay, now see here, if one charge is at the origin, and if one charge is at the origin means, for suppose x1 y1 z1 or x2 y2 z2 is located at 0. Okay, so all those terms are 0. And when x2 minus x1 into ax, y2 minus y1 into ay, z1 minus, z2 minus z1 into az, right? Here x1 y1 z1 is 0, then x2 ax, y2 ay, z2 az, right? Here also x2 square, y2 square, z2 square over 3 by 2. See here, so one charge is at the origin and another is at they existed at somewhere at xyz point. Then the resultant f1 equal to q1 q2 by 4 epsilon x into ax, y into ay, z into az by x square plus y square plus z square. Okay, over 3 by 2. Okay, so already you know for like charges and the same charges having excuse me, of course the same charges repel each other and opposite charges attract each other, right? The same charges, okay, here having identical signs, okay, the force is repulsive. Okay, the same charges always repel each other, and opposite charge, okay, is okay, and is in the same direction. Okay, opposite signs having attract each other. Positive, negative attract each other. Negative, negative repel each other. Okay, it is indicated with a negative sign. Okay, for convenience. See here, 2-point charges. Okay, this is also one of the okay, important problem. Okay, and in the exam point of view, see here, 2-point charges of 2 microcoulombs each. What it means? 2-point charges Q1 and Q2. Okay, let it be. Q1 and Q2. Q1 charge is 10 microcoulomb, Q2 charge is 10 microcoulomb, 2 point charges of 10 microcoulombs each, and of the same sign are situated at 1 point. Okay, the same sign are situated at 1.5 centimeters apart, and that Q1 and Q2 are spaced apart. How much distance? 1.5 centimeters. Okay, 2 point charges of 10 microcoulomb each, and of the same sign are situated at 1.5 centimeters apart. Calculate its magnitude of the repulsive forces. Of course, they are always same sign. Okay, here the same sign means repulsive each other. Okay, opposite sign means attract each other, right? So see here, according to the problem statement, 2 point charges, right? Q1 and Q2 equal to 10 microcoulombs. That is 10 into 10 power minus 6 coulomb. Okay, already you know micro means 10 power minus 6. Okay, how they are aparted? Okay, at the distance of 1.5 centimeters. That is okay. 0.05. Okay, here need to convert that centimeter distance into meters. Okay, remember that point. Here 1.5 centimeters. Okay, and into 10 power minus 2, right? Into 10 power minus 2. Okay, so if it is again converted into the meters, okay, um, how much it is? 0.015 meters. Okay, assume that all the charges are in this space. Of course, these two charges are available in this free space. That's why here we need to consider epsilon naught value as 8.854 into 10 power minus 12. Okay, that is the indirect representation. Okay, epsilon equal to epsilon naught into epsilon r equal to 1. That epsilon naught value is 8.854 into 10 power minus 12. This is the constant value. Okay, remember this point. Okay, next from the statement of the Coulomb's law, F equal to Q1 Q2 by 4 epsilon naught r square, right? So from that Q1 10 microcoulomb, Q2 10 microcoulomb. Okay, 10 into 10 into micro is 10 power minus 12. Okay, 100 into 10 power minus 12 by 4 pi into 8.854. This epsilon naught value is 8.854 into 10 power minus 12 into how much that distance is 0.015 whole square. Okay, okay. On simplification, we get 4 into 10 power minus, okay, plus 3 newtons. Okay, and this much of force acting between that Q1 and Q2 repulsive force, and with this force they repel each other. Okay, since charges of the same sign, okay, the force is, okay, the charges of the same sign, yes or no, the charges of the same sign is the repulsive. For suppose uh, another one is the minus 10 microcoulomb. Okay, that is attractive. Okay, see here another problem. Find the force on charge Q. Find the force on charge Q1. Okay, 450 microcoulomb located at 500 and on x-axis, right? Y equal to 0, z equal to 0. Okay, due to the charge Q2 250 microcoulomb. Okay, and how much force act on that 450 microcoulomb? Due to that 250 microcoulomb, that Q1 is located on the x-axis at a distance of 5 meters. Okay, and Q2 is located at a distance of okay, and Y and Z intersecting point at a point from main. And just this is the situation, like, okay, see here. So just wait. See here, X, Y, Z. Okay, let us assume. Okay, this is X, this is Y, and this is Z. See here, find the space on charge Q1 450 microcoulombs located at which point? 500, right? Okay, let us say this is 1, 2, 3, 4, 5. Okay, at this point 450 microcoulombs is existed. Okay, this is the point Q1, let us assume. And due to point charge Q2 and in Y and Z combination, right? On that okay, on that x equal to 0. Okay, on that x equal to 0 means 0 comma 4 and 5. Okay, let us say this is 4 and let us say this is 5. Of course, this is like this. I mean, the z direction. Okay, this is the intersecting point. This is Q2. Okay, uh, here 250 microcoulombs are there. Okay, this is point Q2, this is the point Q1, and this is the representation like this. And for our assumption, okay, we'll make it like this. Okay, find the force on charge Q1 due to the 250 microcoulombs. Okay, they are spaced apart. How much distance? Okay, you have to calculate. See here, uh, just I have to consolidate that Q1 and Q2 with charges and distances, right? Q1 equal to 450 microcoulombs at a distance of 500. That is R1 equal to how much? Yeah, how much distance from that origin? 5ax, right? 5 because y and z both are 0. Okay. See here, Q2 equal to 250 microcoulombs located at 4, 5. R2 is 4ay and 5az, right? Um, now tell me what is the distance vector from R1 to R2? Distance vector from R1 to R2. Okay, R1 minus R2, right? So R21 equal to distance vector 5 minus. Here is there any x component in the R2? No. Okay, that's why 5 minus 0 of ax. Okay, 0 minus 4 of ay, 0 minus 5 of az. Okay, that is the distance vector 5ax, 4ay, 5az, and its magnitude is square root of 5 minus 0 whole square, x2 minus x1 whole square, right? 5 square. Okay, 0, okay, minus 4 whole square and minus 5 whole square. Okay, the distance between these two. Okay, what is the distance between these two? The distance between these 2 points is how much? Okay, 8.12. Okay, that is 8.12. The distance is 8.12 meters. Okay, now that unit vector is R21 by R21, right? And the distance vector R21 by its magnitude. Right? Its magnitude is already found here. That's why 5ax minus 4a minus 5az by 8.12, or simplification we get this J vector. Now, according to the Coulomb's law, force on Q1 due to the Q2 is F equal to Q1 Q2 by 4 epsilon naught R square. You can just substitute Q1 value, Q2 value, and 4 pi epsilon naught and R21 whole square value. Okay, and 8.21, right? In the direction of unit vector. Okay, on the simplification, we get, see here, okay, 9.4 ax minus 7.6 ay minus 9.4 az newtons. Okay, and at these points, okay, at these points, and 9.4 comma minus 7.65, okay, minus 4.az. Okay, and this much of force. Okay, this much of force acts on, this much of force acts on, and in the direction of. Okay, of course, see here, and 15.43, 15.3. Okay, this much of force acts on that point Q2. Okay, in the direction of 0.615, 0.5a5, 0.615 az in these directions. Okay, that is the conclusion. Get it? Okay, understand these two problems? Okay, in terms of the rectangular coordinates. Next, force due to n number of charges. And so far we consider the 2-point charges, right? Q1 and Q2. But now the situation is extended to n number of charges. And when we consider more than 2 charges, okay, what is the net attractive or repulsion force? Okay, acts on. See here, and when we consider n number of charges Q1, Q2, Q3, and so far we consider only 2 charges, right? Q1 and Q2. But the situation is extended to n number of charges. Okay, consider n number of charges Q1, Q2, Qn. Okay, I shown a figure with association with the distance of R1, R2, R. Okay, and when we consider the charges Q1, Q2, Q3, so on, Qn. Okay, those charges are located away from that origin at a distance of R1, R2, R3, so on, Rn. Let another point of charge Q at a position R. Okay, let it be. And how much force acts on it? Okay, the total force exerted on the point charge q due to the n number of charges. And I mean, this is the reference, so reference point charge. Okay, q1, q2, q3, q2, q4, q5, up to so on qn, and here n number of charges are there. Okay, these n number of charges and how much attractive or repulsion forces acts on that charge q. Okay, that's the point you have to find out here. Okay, the total force exerted, and that may be attraction force or repulsion force, and depending upon the uh, type of charge it is it positive or negative. Okay, the total force acted on the point charge q due to n number of charges satisfied with the principle of superposition. Okay, and that is equal to the vector sum of all the forces exerted. That's why I told you okay, while starting simply that that is the vectorial sum of all the forces exerted on the same charge. Okay, uh, see here, the ratio is also simple. Again, it's from only Coulomb's law. Okay, let the vectors r1, r2, rn, or the distances vector from that q1, q2, qn respectively. Okay, then the forces f1, f2, f1, I mean up to fn are exerted on the q due to that individual point charges from q1, q2, q3 up to so on qn. Yeah, that is the okay picture or way picture from. Okay, then that attraction force or repulsion force on that point charge due to q1, and because of the q1 how much force acts on the q, because of the point charge q2 how much force acts on q. Okay, similarly q3 how much force acts on q. Okay, q4, q5, q6 up to so on qn. Okay, how much force acts on that single point charge q. Okay, individually I have to find out by using Coulomb's law. Later I need to summarize, I mean need to sum all those effects. Okay, that's why here f1 equal to how much force acts on q1, q on q, q1 on q. Okay, f1 equal to q1 by 4 5 epsilon r1 square, f2 equal to q1 q2 by 4 5 epsilon r2 square. Okay, and fn equal to qn by 4 5 epsilon rn square. Okay, the respective unit vectors are of course ar1 equal to r1 by mod r1. Okay, r2 by mod r2. Okay, this is also hence the total force on q is according to the principle of superposition theorem, f equal to f1 plus f2 plus f3 up to so on n. Simply I am replacing f1 with q1 q2 by 4 5 epsilon r1 square ar1 is replaced with r by mod r, right? So q1 q2 by 4 epsilon r1 square of ar, q1 q2 by 4 epsilon r2 square of ar2 up to so on q into qn by 4 epsilon rn square into ar. Okay, now this is the net force acts on that point charge q. Okay, net force acts on that point charge q due to that individual charges q1, q2, q3 up to so on qn. Okay, here I take the word q by 4 epsilon as a common, and that q1, q2, q3, this is the variable, right? I mean here subscript is the variable, right? 1 2 3 up to so on n. That's why summation of n equal to 1 to n. Okay, summation of n equal to 1 to n. Okay, qn of qn, and where n varies, q1, q2, q3, q4, right? Okay, into of course the unit vector along the direction is also vary, right? So that's why a of rn, that is also varied. Okay, n is varied, and rn square, this is also varied. Okay, identify that variable points. Okay, variable, this is also variable, this is also variable. Okay, that's why n equal to 1 to n qn a of rn by rn square. Okay, this is the point of attraction or repulsion forces because of the multiple charges, okay, on the fixed charge. Get it? Okay, that's all. Okay, now see one problem. See here, four. Okay, I mean, this is also it's very important. See here, four concentrated charges q1, q2, q3, q4 are located at vertices of rectangle. Okay, vertices of rectangle. Okay, identify that point. Okay, remember that point. The length of the rectangle, and how much the length of the rectangle is 5 centimeters, and breadth of the rectangle is 2 centimeters. Okay, Find the magnitude and direction of the resultant force on Q1. Okay, here they consider four concentrated charges Q1, Q2, Q3, Q4 on a rectangle. Okay, let us say Q1, Q2, Q3, Q4. Okay, and okay, the length of the rectangle is the length of the rectangle. The length of the rectangle is 5 centimeters, 5 centimeters, 5 centimeters, and 5 centimeters. And the breadth of the rectangle is 2 centimeters. Breadth of the rectangle means okay. Oh, sorry. This is the length. Okay, this is the 5 centimeters, and breadth. This is 2 centimeters. Okay, this is not a cube. Okay, that length and this is the width is mentioned as a breadth here 2 centimeters. This is 5 centimeters length and width. Okay, the mention is the length and breadth. Okay, see here now what they are asking, how much force acts on and how much force acts on this Q1 due to and the attraction repulsion forces on Q1 due to Q2, sorry, Q2, Q3, and Q4. Okay. Again, the Coulomb's law. Okay. And Q1 to Q2, next Q1 to Q3, and the first case is F12 equal to okay, Q1, Q2 by 4 epsilon naught R square. Second case, F13. Next case, F14. That's all. Okay. See here. Let the rectangle with length of 0.05 meters. Okay, here 5 centimeters. That's why it is converted into meters. Remember that point. And breadth or width is 0.2 meters. Ready? Okay, placed on the XY plane, right? The four charges are located at the four vertices of the rectangle in a free space. Okay, that's why see here Q1 0.3 microcoulombs, right? Which is located at 0.05, 0.02, and 0. Okay. Similarly, Q2, which is located at 2 microcoulombs. Okay. Q3 minus 0.3 microcoulombs at 0, 0, 0. Okay. And this is all assumption, right? See here, this is the rectangle. Okay. This is Q1, and here this is my assumption. Okay. Q3, Q4. Okay. Let us assume this is the X and this is the Y. Okay, this is the X and this is the Y. Okay, so this is the point where 0 comma 0 comma 0. Okay, and Q3 is located at minus 0.3 Q3. Okay, 0.3 microcoulomb. Okay, so see here Q3 to Q1 direction is like this. That's why, and in this point of view, this is called minus 0.3 microcoulomb. Okay. Okay. Similarly, so this is the distance of 5 centimeters, and this is the distance of 2 centimeters. That's why Q1 location. Can you tell me the location of the Q1? Q1. Okay. X direction is 0.05. Okay. 0.05, and Y direction is 2 centimeters, 0.02, and Z is 0. Similarly, Q2. Okay. Q2, and this is the point. Okay, is there any extension or is it elsewhere? No. Okay, only this direction, right? That's why this is 0 comma and x-axis, y-axis, and z-axis notation. Okay, comma, this is the point of at a distance of Q4. It is 0.02. Okay, similarly Q3 0, 0, 0. Similarly Q4 again 0.5. Okay, 0.5. Okay, and further is no there. Okay, that's why 0, 0 comma 0. Okay. Okay, I think this is the depiction. See here, or simply we consider maybe from this expression also, and from this diagram also. See here, Q1, Q2, Q3, Q4. Okay, and the forces are depicted like this in the X and Y and Z directions. Okay. Again, according to the Coulomb's law, by using superposition principle, F equal to individual. Okay, you may directly found individual. So F equal to Q1 Q2 by 4 pi epsilon naught R21 whole square. F13 equal to Q1 Q3 by R31 whole square. Okay, Q1 Q4 by R41 whole square. Just to have to substitute and simplify. So R21 is already 2 to 1. Okay, and x2 minus x1, y2 minus y1, right? And the distance vector a of r21, see here. So from that point 0.05 ax by its magnitude square root of 0.05 whole square and root over both are cancelled, so that is just 0.5. Resultant is ax. Similarly r31, okay, similarly r41, and finally you have to substitute that q1. Okay, and how much force acts on q1, that you have to separate here. So Q1 by 4 pi epsilon naught, Q2 R21 AR21, Q3 R31 AR31, Q4 R41 AR41. Simply substitute and simplify. We get the net force acts on that point charge Q1 because of charges Q2, Q3, and Q4. Okay, Q2, Q3, and Q4, and this much of force acts on that point charge Q1. Yeah. Okay, and that's all about Coulomb's law and associated possibilities and problems. Okay, so next concept is electric field intensity. Okay, electric field intensity. Okay, see here. See here electric field intensity. Okay, and from so far we'll learn about the Coulomb's law. Okay, and how much force acts on different charges. So the next concept is electric field intensity. Okay, and the next concepts are electric field intensity, charge density. Okay, okay, different types of charge densities. See here, and the electric field intensity means what is the field intensity? Okay, just to classify that. Electric field intensity. Okay, what is meant by intensity? What is meant by density? Okay, what is meant by charge density? What is meant by field intensity? Density is always per unit area. Okay, how much charge is distributed, right? There is a charge density. Here also the same, field intensity. Okay, and how much force exerted on unit charge in an electric field. And when we consider in the electric field, how much force exerted on particular unit charge, that is called electric field intensity. Okay, see here how they stated. The force exerted on a unit charge in electric field is called electric field intensity. Okay, you feel that terms. If you feel that terms, then it is very convenient to understand. Okay, the force exerted on unit charge in electric field intensity called electric field intensity or electric field strength, and both are same, of course. Okay, the electric field intensity at any point due to the point charge is proportional to the magnitude of the charge, of course. That is already Okay, the electric field intensity E or simply force. Okay, F equal to Q1 Q2 by 4 epsilon r square. That is the same holds good here. The electric field intensity at any point due to the point charge is proportional to the magnitude of the charge, just like F proportional to Q1 Q2, and instead proportional to the square of the distance between them. Okay, Here also the same, okay, proportional to the square of the distance from the charge to that point. Okay, if the point charge is brought near another charge, it experiences some attractive or repulsion forces much more. Okay, the field where the charge exerts a force on any another charge is called electric field, field of the charge. Okay, just like that force, but they mentioned in terms of charge. Okay, from the definition of force exerted in a unit charge statement. See here, consider a single point charge Q2 located at any point near the other fixed point charge Q1. As shown in figure, the electric field strength due to the point charge Q1 at the point charge Q2 is defined as per the force of unit charge Q2. That is, uh, of course, in general, F equal to Q1 Q2 by 4 pi epsilon naught R square. That is the known formula, right? F proportional to or F equal to Q1 Q2 by 4 pi epsilon naught R square. Okay, but according to the definition of electric field strength, E equal to force exerted on point charge. Okay, so E equal to F by Q. That is the definition, right? E equal to F by Q. And a force exerted on the point charge. Okay, mathematically that is represented as electric field intensity E equal to force exerted on point charge, force F exerted on point charge Q2. Okay, see here, what is meant by F1? Okay, or what is meant by F according to the Coulomb's law? F equal to Q1 Q2 by 4 pi epsilon naught R square. Q1 Q2 by 4 pi epsilon naught R square. Okay, when we substitute F equal to Q1 Q2, F equal to Q1 Q2 by 4 pi epsilon naught R square directly here, Q1 Q2 by, see here, F equal to Q1 Q2 by 4 pi epsilon naught R square, and Q2 Q2 cancel each other. Only it remains Q1 on the denominator, 4 pi epsilon naught R square in the direction of AR. Is it clear? Just here I am substituting Coulomb's law statement F equal to, okay, just I am substituting F equal to Q1 Q2 by 4 pi epsilon R square divided by again Q2 Q2 cancel, only Q1 by 4 pi epsilon naught R square. Okay, from that E equal to Q by or Q1 by 4 pi epsilon R12 square in the direction of R12. Okay, where R12 equal to R2 minus R1 is the radial distance from the Q1 and Q2. Here the fixed charge is Q1 becomes the source of the force acting on Q2. Okay, and here uh, uh, observe this point. Okay, here fixed charge Q1 becomes the source of the force acting on Q2. And from the okay, because of that Q1, some force acting on that charge Q2. Okay, the vector field E gives that force per unit charge anywhere in space. Okay, in general, the electric field intensity is defined as E equal to F by Q. Okay, newtons per coulomb. Okay, limit Q tends to 0 until. Okay, see here the vector field. See here, this is the Q1 and this is the point Q2. Okay, these are separated by distance R. Okay, so the vector field, the electric field intensity is proportional to the force and that direction along the force. Okay, it can be seen that the electric field intensity is symmetrical in the radial direction. Okay, it distributes equally in all directions. This is called isotropic. Okay, it can be seen that the electric field intensity is symmetrical in the radial direction and varies inversely with the square of the distance between them. Although already you know that's the relation. Okay, see here E equal to Q by, and from that derivation E equal to F by Q, F equal to Q1 Q2 by 4 pi epsilon naught R square. when we substitute f equal to q1 q2, the q2 is cancelled, q by 4 pi epsilon naught r square. Okay, so resulting is electric field intensity equal to q by 4 pi epsilon r square. The direction of E along the radial distance from the positive charge q1. Okay, the electric field has the same intensity at all points because it radiates equally in all directions, right? So E equal to q by 4 pi epsilon r square. Here no need of single direction vector. Okay, that's why it is not mentioned here. A Cartesian coordinate system, the electric field intensity at the point x2 y2 z2 due to that point charge q1, which is located at x1 y1 z1. Simply we get E equal to q by 4 pi epsilon, that r2 is mentioned as x2 minus x1 ax, y2 minus y1 ay. Okay, z2 minus z1 az by x2 minus x1 whole square, y2 minus y1 whole square, z2 minus z1 whole square, or 3 by 2, right? Okay, that is the resultant electric field. Okay. Similarly, the electric field intensity due to n number of charges, and when we consider the n number of charges, that is also same. That is also the algebraic sum of, and just like superposition principle. Okay, algebraic sum of all that charges. Okay, see here, see this problem. Okay, that is also a derivation like the force acts on a number of charges. Okay, no, okay, don't worry about it. About it, it is that much of that is not much of important. See here. Determine the electric field E at the origin due to the point charge of 54.9 nanocoulomb located at minus 4, 5, 3 in air. Okay, actually the point is located in space with point charge of 54.94 nanocoulomb. Determine the electric field due to the charge. Okay, so here Q equal to 54.9 nanocoulomb at point charge of minus 4, 5, 3. Then according to the definition, E equal to Q by 4 epsilon naught r square of AR. So simply substitute in air epsilon equal to epsilon naught. Here no need to consider epsilon r because for air, that's why that epsilon r value is 1. Okay, E equal to 54.9 nanocoulomb, right? 54.9 into 10 power minus 9 by 4 epsilon naught r. Here r equal to, okay, from the origin, right? From the origin. Okay. That's why 0 minus, okay, 0 minus 4 ax, 0 minus 5 ay, 0 minus 3 az, right? From that 4ax minus 5a minus 3az. Okay, its mod value is square root of 4a square minus 5 square minus 3 square equal to 50. Okay, from that unit vector is 4ax 5ay 3az by root over 50. Simply substitute those values, we get, okay, this much of force in the direction of ax ay az is acted. Okay, that is the electric field intensity. Next, charge distributions. Okay, see here, this is very important. Okay, this is quite important and frequently asked question in the final examination. Okay, charge distributions. Okay, the electric charge in the medium can be of any of the following forms, and I mean it may any form it may be. The electric charge in a medium, in free space, medium and medium, or I mean any free space or any medium. It can be the following forms, maybe in the form of point charge, maybe in the form of integration of those points. See here. Okay, this is also very systematic. Okay, this is the point charge means single point. Okay, line charge means point charges integration. Okay, this is the point charge. This is the point charge. Okay, and see here, and one these two one all these are the point charges. Okay, And when these charges are combined, okay, how may look, it's like, okay, just like a line charge, right? From the surface charge, okay, this is the line charge, okay, which is having, for suppose the charge in that horizontal direction and vertical direction, okay, this is called some surface charge, and all these are again points, right? Okay, in the direction of length and width. And when we consider its breadth also, that is called volume charge. Length, width, and breadth. Okay, see here, this is called volume. Okay, line to, when we integrate all the point charges in a sequence, that forms a line, that is a line charge. Okay, when the same line in both x and y directions we consider and form as a sheet, that is called surface charge. And in the direction of breadth also we consider, the length, width, and breadth, then it is considered as a volume charge. Did you get it? Okay. Electric charge in the medium can be of any of the following forms as point charge, line charge, surface charge, and volume charge. The total charge caused by that charge distribution can be obtained by integrating the individual okay, charge elements, okay, over the entire charge distribution. Okay, that is the point, right? Point charge means the single point charge when we integrate in single direction, like a very thin line, that is called line charge. When we integrate that thin line in both horizontal and vertical direction as let it be assumed as a rectangular sheet, that is called surface charge, which is also having some volume, that is called a volume charge. Okay. Okay. Best example, can you tell me that best examples for the point charge? Point charge. Okay. Can I consider that electron as a point charge? Single electron. Can I consider that single electron as a point charge? Yes, of course. Okay, the single electron having negative charge. Okay, single proton having positive charge. Okay, okay, that is the point charge example. And line charge, when I'm integrating that point charges, and just like a filament, just like a filament. Okay, did you observe that filament? It's very thin. Okay, single line of high resistance wire, right? High resistance wire or segment. That is the line charge. And surface charge means, can I consider that surface of the capacitor? Can I consider the surface of the capacitor? That is called a surface charge. And volume charge means which is having some thickness also. Which one is the best example of that volume charge? Can I consider that ozone layer? Ozone layer of space. Okay, that is invisible, but that is the cluster of charge distributions over length, width, and thickness. That is the volume charge. Okay, these are the four best examples of that point line surface and volume charges. See here the point charge. Okay, small amount of the charge Q occupying that infinitesimal volume is called point charge. The unit okay, I think as thin as possible. Okay, the unit is of course the unit also is charge unit is always coulomb. Okay, its value can be either positive or negative. Okay, already I told you, no. Okay, uh, what is meant by single electron charge. Next, line charge. A line charge, a charge uniformly distributed along the line is called a line charge. The line charge density is the charge per unit length. It is expressed as a total line charge per unit length. Okay, remember this relation. It is very simple. Line charge, okay, total line charge by, okay, how much it contains the length. Okay, Q by L. Okay, from that, okay, line charge density is the rho L. Okay, charge density. Okay. If the line charge density is a function of the length, then the differential charge dq on a differential length of dl is given by here dq equal to rho L dl. So C q equal to rho L into rho L, right? So when you consider that its differential length, dq equal to rho L dl. Okay. The total charge density, how much? Integrate on both sides. Q equal to integral rho L dl. Okay, remember this relation. Integration along the line is called a line integration. This line may be infinite length. If the line is in the form of closed path, then Q equal to integral, closed integral. Okay, this is closed integral of rho L dl coulombs. Similarly, surface charge. Okay, the total surface charge by total surface area Q by S. Okay, when we consider its charge density equal to dq by So this is the relation Q equal to rho S into S. Okay, when we consider its differential length, dq equal to rho S ds. Okay, so total charge density integrating on both sides, Q equal to integral dq equal to integral rho S ds. Similarly, for volume charge, okay, total volume charge by its volume. So rho v equal to notations. Remember this notation. Point charge doesn't have any okay permanent notation, but line charge having rho l, surface charge having rho s, and volume charge having rho v. Total volume charge by volume equal to rho v equal to q by v. So q equal to rho v into v, and differential manner dq equal to rho v into dv. Okay, dq equal to rho v into dv. Okay, the total charges integrating on both sides, q equal to volume integral of dq, integral of rho v into dv coulombs. Integration over a volume equal volume integration. Okay, that's all. Okay, okay, that's all about today's class. Okay, this is the problem associated to about statements. Okay, we will see in that in next class. Okay, that's all about today's class. I will continue in the next class. If you have any doubts, okay, um, just ping me on WhatsApp. Okay, or any other general discussion, or okay, if you have any doubts, okay, regarding to career, or regarding to I mean that outcoming opportunities. Okay, uh, and if you are anybody interested, okay, then ping me on WhatsApp. Okay, I will and if you are interested, you may connect it with Zoom. Okay, okay, that's all about today's class. I will continue in the next class. Thank you.